One problem of geometry I have seen is there are too many things there to study. No? We have what are called axioms. Axioms are actually self-truths. That means you make that statement and say it is true. There is no proof, there is no logic. I am saying for me it appears to be true. Therefore, for you also it should appear to be true. There is no other explanation for it. No? So that is known as an axiom. Axiom is stated as proved, stated as correct, stated as assumed. It is an assumption. Actually, it is an assumption, but it is a universal, assumed as universal truth. It is an axiom. Okay. Then, using these axioms, we prove some lemmas. Lemmas are small theorems, very small theorems. I can give you proof for that. They are true actually, but I can give you proof for them in 1 or 2 lines only. Very simple to prove, very simple to understand, but then they are of great significance because I can use the lemmas as the basis for proving further things. So they are called lemmas. Next comes the actual theorems. Now, theorems are the most important parts of geometry or even algebra, for example, any subject or even calculus. Is we state a fact saying if this is this, then that is that or whatever, and we are going to give a systematic proof saying why I am saying that. So we have to provide a proof for the theorem. But when we have to provide a proof for the theorem, many times what is there as a picture for the theorem is not enough. We need to add some further details into the picture. What are called constructions. In fact, most of the geometric theorems require some sort of construction. Construction is adding some lines, adding a circle, adding an altitude. We add, and in fact, we show that as a dashed line to say that this is what I have constructed to be able to prove this theorem. Original theorem didn't have that diagram, but I've added some additional details to that picture. That is a construction. That is one aspect which is there, which you have seen also. Now I want to add another aspect of the same construction, which has not been given in a book. I will call it deconstruction. So in fact, our problem has been not in construction, but in deconstruction, opposite of construction. Now the diagram as originally given as per the theorem has got a few lines and circles or whatever. It has got some details. Correct? No? The problem is it's too complicated. For the human eye, there are so many things which are presented as the original picture. Now, our focus should be on one part of the picture. Correct? So you deconstruct the rest of it. That is, remove the part of the picture. Removing, not addition, is a subtraction, is removal. So we would like to look at only some aspects of the picture, which I can perhaps show it with a different ink for you to understand. I am saying for the next discussion that I am going to do, please don't look at the entire picture here, but only look at that part of the picture which I have deconstructed, out of the original picture, and that is what is interesting for the proof. That is deconstruction. So we do a deconstruction first. So we reduce the picture from too many details to the required number of details. On top of that, we add constructions. So on this, now I am going to construct. That means now you have deconstruction, removing some uninteresting parts and adding a very important part which was not even there in the original picture. Then I can give you the proof in a very simple way. Is to do this construction, deconstruction and construction. Deconstruction is only a way of looking at things, saying don't look at unnecessary detail. When you look at something, when you look at an object, look at only the interesting parts of the object. Interesting part may be different at different points of time or different view, but today what is interesting for you is what the part that you have to look at. Ignore the rest. Ignoring rest of the picture is an important part of learning. So that is deconstruction, then construction. So for theorem we give a proof. Once the proof is given, everybody understands this is fine, this is correct, Pythagoras Theorem is correct. sum of squares on two sides of a rectangle triangle is equal to square on the hypotenuse, everything is fine, no problem. But then based on that, I can prove a couple of small side things, small things which are actually called corollaries. Corollaries are almost like theorems, but then they are not so important from the point of view of history, historical record. Theorems are very important because they are going to be remembered for a long time in that particular fashion. Corollaries are side products, is like side product of an industry, side product of theorems, which might be useful or which might be interesting or which might look even beautiful actually to look at. Many times you look at beauty itself as part of science. Mathematical research, even though originally it started because of necessity, saying I need to study heavenly bodies or I want to measure area of a triangle, the actual need for it. But then later on, many parts of geometry you find something beautiful saying, my goodness, it looks so nice, and so research may lead to some beauty also, which may not be useful today, or may not even be useful tomorrow, doesn't matter, but at least it looks beautiful and nice. So I would like to look at it, those kind of things. So corollaries can give you that kind of beauty also. Theorems themselves give you a lot of beauty to look at and understand, and they're fantastic. Corollaries are additional things. So when somebody, mathematician, gives a new theorem, obviously we expect him to give you a proof for it. And we expect, and he says part of the proof is in some axioms and some one or two small lemmas that he might prove or not. Then he gives you the actual proof using some kind of construction, right? So that he has got to provide. But many times what happens, there are some mathematicians who are far thinking, ahead, saying, I know this is the theorem, but I don't know how to prove it. He says, I will make a statement of a theorem, which is correct. You can see it is correct. I can see it is correct. You can see it is correct. But I don't have a proof for it. I can't give you a proof for it. If somebody, one of you can give the proof for it, you are welcome. Very nice, very nice. But this is a beautiful theorem. So such statements, which are actually not theorems, but they are absolute truths. In that sense, they are correct. They are actually called conjectures. Conjectures are statements some scientist makes for which there is no yet proof as yet, but it might be provided by somebody else in future. One example of a conjecture I'll tell you. Newton's law of gravitation, when he presented, saying a sun actually attracts earth with a force equal to G1 M2 M1 M2 by R squared or whatever the equation he gave, that was only a conjecture. Who knew whether sun attracted earth or what is the force? Nobody knew those facts. He just assumed them, right? And he made a conjecture out of that. Law of gravitation was a conjecture when he gave. So it was only a conjecture of gravitation when Newton presented it. But later on, a few decades later, somebody was able to actually verify it in a laboratory condition that actually there is an attraction between two objects with two different masses, and the force is exactly like what Newton predicted. So now we don't call it a conjecture of planetary motion, we call it a law of planetary motion, or we call it a law of gravitation. Conjecture becomes a law once it has been proven either through observations or experimentation or through formal proof. And today mathematics requires what are called not just a proof, is a rigorous proof. In fact, half the problems that you are going to face in mathematics as of today is to provide rigorous proofs. Proofs should not be intuitive. Intuitively you say, no, this is there, no, that will be like, I know it will be like that, but you can't make a statement like that based on intuition. It has to be based on facts. It has to be based on previous theorems which have been proven. So that is a rigorous proof. So providing rigorous proof is a part of the exercise in mathematics. Okay. So all these have to be done. So now we are going to start with geometry's original axioms that Euclid made, original assumptions, which all of us take for granted. We have to always take axioms for granted, saying they are true. There is no questions about it. We can't ask questions about it, right? So that is there. Then we look at some theorems and see how that actually they are proven. Any deconstruction necessary first to clear our mind of unnecessary detail, and then any construction which is actually going to be required as part of the proof. And why that particular construction has to be there also is a question, no? Because I want to look at a proof of a theorem, whether it is Pythagoras theorem or Thales theorem, doesn't matter. I want to look at it from his point of view when he proved it, not today when the proof is already available in a book. I just want to memorize it. It's not that. I'm not looking at memorization of proof. I'm more looking at saying, supposing Pythagoras theorem was only a conjecture as of today. Pythagoras has stated that conjecture, nobody has proved it. You have to prove it today. Tell me how you are going to go about doing it is the way you have to think when you look at a particular proof, is what I want to do. Okay? So now we'll start with that. Where does the geometry itself start? Is the question. Obviously it starts with a point on a plane. So we start with that. So what is the first object that we see or visualize? Is a point on a plane. A plane has got infinite number of points. You can have any number, you can have a point anywhere in the plane, any number of points, but we have a point on a plane. So the first axiom is a point on a plane has zero dimension. What is dimension? Is width and height and diameter and radius, whatever you think of, is zero. Everything is zero there. So point is, there is no width for the point. So there is no height for the point. It is zero dimension, zero height, zero width. But point is there. So you visualize a point on a plane. So that's the first axiom. I am telling you, point on a plane is there. Is correct. You have to assume it is correct, right? So now next is, we go beyond the point, is a line. Line, like I said, we are actually talking of straight lines, but I don't want to keep on saying straight line, straight line, straight line, like ardhaja, ardhaja, ardhaja. I want to call it a line. So when I say line, it is a straight line. But if you don't want a straight line, I would call it curved line. No? So I can have a curved line also. So you can have a curved line, or you can have a straight line. So straight line is line. So what is a line? Line is a series of points which are joined together of zero dimension. Of course, now this has got a dimension. When I write on the board, it has got a thickness also. That is only for our visibility. But assume that it is zero height. So I draw a line in one direction, maybe east or something. So east is the direction I have chosen to draw this line. By joining a series of points in one direction, that becomes a line. So this is a line. So this is the second axiom, is a line. Line joins a series of points in one direction. That is an axiom. I am assuming it is going to be true. You have to assume it is correct. Okay? We assume that. Now what is the third axiom? Right? Before we go to the third axiom, now as soon as you have different points on the line, I can measure something called a distance between 2 points. So I can have any 2 points on the line, right? You can call them A and B. Remember, these notations also have taken some time to evolve in the history of mathematics. People used to refer them not as A and B, but as number of cows, number of buffaloes, number of kilos of rice, number of, they used to refer it by full words, full sentences. But then later on, as algebra progressed, part of the algebra is notation, no? Saying we use symbols to represent quantities. And the simplest symbols that you can use are alphabet letters. And alphabet letters, we use English, of course, most commonly. But we also happen to use Greek letters, because Greek is the original language, of mathematics evolution. So, like we use letters like alpha, beta, gamma, and so on. So, delta, correct. We use those also. No questions on that. Right? And we have some very specific letters which I will mention, Greek letters which are of universal importance, that we will come to later. So you got 2 points. As soon as you have 2 points on a line, we define what is known as a distance between the 2 points. So we have a distance. And you can measure the distance. Actually, you can measure the distance in terms of some units like centimeters or millimeters or whatever, feet, you can measure. So the distance is there. Then, which means distance can be one distance or two distances or three distances and so on. So which means the first idea which came to people, mathematicians, was that when I have points on a line, I can map points on a line to natural numbers. So we have numbers which represent values like 1, 2, 3, 4, etc. I am writing them in Arabic numerals, but then originally they were written in Greek representation. One was I, V, and so on. VI. Remember, that's how people are writing numbers. The Greek notation. The entire Greek mathematics is written with that as a number system. So 1, 2, 3, 4. I can map every number to one unique point on the number system, which are equidistant from each other. So I got 1, 2, 3, practically like points on a line. Points on a line represent the natural numbers. Now natural numbers have one property. If you look at number system, so I would briefly look at number system before we go to next topic in geometry itself. Number system, first is natural numbers. This is the oldest way of representing numbers, is a way of counting. It's actually come out of counting, which has got 1, 2, 3, etc. Whichever representation that you write, they are called natural numbers. And when you have two natural numbers, I have got 3 potatoes, you give me 5 potatoes, totally I will have 8 potatoes. You understand? I can add 2 natural numbers, I'll get a third natural number. I can multiply 2 natural numbers, I get a third natural number. So these natural numbers are supposed to be closed with respect to addition and multiplication. That means adding 2 natural numbers, I'll still get a natural number. Remember, infinity is not a number, but I can have as large a number as I want. Whatever numbers you multiply will still be a number only. So no questions on that. That's why they are known as closed with respect to addition and multiplication. Regardless of which 2 natural numbers you take and add or multiply, you will still be left with a natural number only as a result. But when you look at subtraction, we have a small problem. Subtraction, I take 2 natural numbers and subtract one from the other. I have 5 mangoes and I give you 2 mangoes. How many mangoes I am left with? Is 5 minus 2 is 3, correct? No question. Is a natural number. But then I can't write, supposing you say I want to do A minus B, I can do the subtraction only if A is bigger than B. If A is not bigger than B, I will not be able to do the subtraction, correct? No? So that itself, that bigger business itself is a property of these natural numbers, which is known as ordering. Natural numbers are ordered, which means any 2 natural numbers, if you have A and B, if you have 2 natural numbers A and B, only one possibility of 3 which can be true. Only one, exactly one. First possibility is A is equal to B, both are same, is one possibility, right? Whatever the numbers are, both are same. Then second possibility is A is bigger than B, and third possibility is A is less than B. There cannot be any other possibility. That is known as ordering. And ordering also implies another axiom we can think of. If A is greater than B and B is greater than C, so this is the fourth statement. If A is greater than B and B is greater than C, then A is greater than C. Really speaking, this fourth axiom for ordering can be simply looked at in this number line. I can call it a number line. Very simple way. When is a number bigger than the other number, it is to the right of this number. When it is smaller, it is to the left. All smaller numbers are to the left, bigger numbers are to the right. So if I have got one number to the right, another number still to the right, obviously it is to the right of the original number. So that is the meaning of A greater than B and B greater than C, saying A is greater than C. Correct now? You understand? So ordering. So that is order. Now how do we achieve this closure or ordering or division? Division is the next problem. When you come to division, I can do division provided is an exact multiple. I can do 6 by 3. Supposing I have got 6 coconuts, I want to distribute it among 3 people, I give 2 coconuts each. Perfect, no problem. But the problem comes, I have only 5 coconuts and I have to distribute among 3 people. How do I? You have to break the coconut, take a piece, and so you understand. That is known as a fraction. So fraction is breaking up a number into pieces, one number into pieces. So that we add that to the list of numbers that we have. In fact, any point in between these numbers, natural numbers, you can see is something like that. Like exactly between 2 and 3 what we have is 5 by 2. 5 by 2 is the point, is the center of between 2 and 3, correct? No, is 5 by 2. So that is a fraction. So when you take fractions also, so we add that as part of the numbers, and fractions have the same properties for addition, is close with respect to addition. Add any 2 fractions, you will get a fraction. And they are also ordered. If one fraction is bigger than second one, which is bigger than the third one, then the first one is bigger than the third one, and so on. So they have the same property for ordering and closure. So which means I can add that as part of my set of numbers that I want to deal with. Because they have the same properties, they are very rational to add. No? So they are called rational numbers. So next set of numbers that people looked at is rational numbers. After natural numbers, rational numbers are all numbers which can be expressed as ratio of 2 numbers, both of them are integers. So P by Q, correct? Regardless of what value of P and what value of Q, you got rational numbers. So I can add and multiply, it will be close. When I subtract, I still have the old problem that I should always subtract the lower value from the higher value. I can do subtraction. Now when I divide, no problem, because I still get a rational number only. So rational numbers added division as an additional facility for doing computations, correct? No? And the ancient Greek mathematicians of 3rd century BC up to 1st century Christian era, they were dealing with rational numbers only. But then we have another small issue of these rational numbers. Not all points are rational. No? So we get some points here which can never be expressed as a ratio of two numbers. Obviously they exist, they are there on the line. No? These numbers exist, but they are not rational. No? You understand? They cannot be expressed as a ratio, and those points are actually called irrational. Irrational numbers are numbers which cannot be expressed as a fraction. Okay? Now, how do we find what is an irrational number? Give me one example of an irrational number. Square root 2 is probably the first irrational number you want to look at. Square root 2 cannot be expressed as a fraction, correct? But it is a proper number. It is between 1 and 2, 1.41, blah, 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 4142 something. No? It's a point between 1 and 2. So that point does exist on this line, but then it is not rational. They are actually called irrational numbers. So Greeks worked with only irrational number system for hundreds of years, and they were able to prove all their theorems, everything with only irrational numbers. Remember, still they did not have a concept of negative numbers. They did not have a concept of zero. That did not exist. That was introduced much later, in the beginning of Christian era. Indian mathematicians introduced the decimal system. They introduced the zero into that system. Once you had the zero and negative, you can add subtraction also as an operation on numbers. And once you do that, what you get, the points on a line becomes real. real number system. So real number system includes both irrational and rational numbers and negative numbers and positive numbers. Since it is really a point on this axis, we call it a real number. No? If it's not a point on the axis, you say, look, it is not real. It is only imaginary. In fact, irrational itself is imaginary to start with. But then we are saying any point which is not on the real line, this is a real line now. It became a real line. Any point which is not on the real line is only imaginary. So that we'll see what is this imaginary, how it comes about. We'll see at a later date. But basically, all I am saying is that once you say I got a point on a line, can represent any real number in the real number system, whether it is rational or irrational. So that is the beginning of geometry, correct? So we'll come back to geometry topic, saying I've got a line now, where if I got a couple of points, I can measure the distance between the 2 points. That's all I have achieved, correct? Now once you have one line, now we go on to 2 lines. So, what can 2 lines do? You have seen one line. One line can get you the real axis, has got you the real axis. Supposing I got 2 lines, what can be done? Now there are 2 possibilities here. First possibility is both lines are drawn in the same direction, same east. They are actually then known as parallel. They never meet. One thing about these 2 lines which are in parallel, axiom, parallel lines never meet. It's an axiom. It is true, but then I have to state it, I have to say it is an axiom. They never meet. And then one side axiom to that is, if I have 2 points, one on either of these 2 lines, and measure the distance between the 2 points, what I do is, I get a minimum possible distance between 2 parallel lines, is known as the distance between the 2 parallel lines. I can have a bigger distance, but then I'm going to have one minimum distance, no? Straight computation. So that minimum distance is known as the distance between 2 parallel lines. Okay. So that is a question of parallel. Now we come to case 3b. 2 lines which are not parallel. That means they intersect. Correct. So first way of looking at it is, I got one line. I have drawn one line in one direction. Now other line I will draw from the same point, but in a different direction. Correct. So if you think of that original point as by a name, I will call it O is the point, name of the point. And the original direction I have drawn is drawn towards a point called, let's say, A. The new line I have drawn will be towards a point called B. Correct. Now what is the difference between these 2 lines? The question is the direction in which they have been drawn. No? So the change of direction, if I can give some measure for it, that change of direction is known as the angle. Angle between the lines. Angle between 2 lines is known as the change of direction for the 2 lines. In the case of parallel lines, there is no direction change, so angle is 0. Actually there angle is 0, whereas here there is going to be one angle. So what is that angle? Now how do we measure that angle is a question. Okay. Yeah. Now I am saying, what do we do about this angle? Now, how do we measure this angle was a question which Greek philosophers had to address first before we proceed with the rest of geometry. No? So obviously we have our basis, the entire basis of mathematics has been Mesopotamian mathematics, Mesopotamian mathematics, which they used, unlike us, they used a hexadecimal system of numbers. Hexadecimal system is, base is 60, not 10. Base is 60. They use a 60 base as the base for their number system. So 60 It's a vague number, but they liked that number, so they used that. And since most of the computations were done at that time using this hexadecimal base system, so 60 became very important number at that time. For example, when these astronomers wanted to divide 1 hour into some n minutes, for example, I want to divide that. How many minutes should we have for our 60? Because that is a number everybody knows. Well-known number, like 10 fingers today. 10 is well known. That time, mathematical computations, anything, say you want a number, 60. Anybody ask a question, what is the next number? 60. So same way, if I want to divide each minute into seconds, and how many seconds should we have? 60 seconds. And now angle, when I change of direction, I do a complete change of direction. That means I start with one direction, east, correct? Now I go around completely, back to east again. That means I have an angle which is the full angle, complete angle. Now that complete angle should have a value, when you want to measure this angle. So complete angle, for some reason they said we'll set it as 6 multiplied by 60, which is 360 degrees. Complete angle is 360 degrees. It's actually 6 times that base, 60 base. And obviously, when you say complete angle is 60 degrees, half of that complete angle, that means a line to the west, that half, if you take that half, and that half will be 180 degrees. So angle is measured as degrees, and half the angle is, complete angle is 360, half the angle is 180 degrees, and 1/4 of the angle is exactly to the north, direction is north. That angle is 90 degrees. 90 degrees is also known as a right angle. So that's how we measure the angles as degrees. So we have now 2 lines at an angle. We have measured the angle and saying that is so many degrees. We can measure it, no problem. We can put a number, 45 degrees, 60 degrees. So we can have 2 lines in which are inclined at any angle that we want, 0 to 360 degrees. That is the angle. So this is on 2 lines which are intersecting at a point. Now the same 2 lines, we get some more interesting properties of the 2 lines. We'll study that next. As 3C. All we do here is, I got one line to start with, to east. I draw one other line at an angle, not north, could be anywhere, probably northeast or something. Now I can produce this. So this is a construction. I want to do a construction on this and produce the east line towards the west also. Right? And produce the second line backwards. Correct? So now I got 4 angles. Now you can see I got 4 angles. Out of these 4 angles, some couple of interesting observations. One is between east to west, I got 180 degrees. Correct? No questions on that. Same way, from the second line to the extension of the second line, I have 180 degrees. There are 2 180 degrees there. Right? And out of the 2 180 degrees, you can see there is a common part. Correct? You remove that common part, I get 2 angles now. That means on 2 lines, if you look at as a separate picture maybe, I got 2 lines. I got an angle here between the 2 lines, and there is an opposite angle which must be equal, because added with the same angle, both produce 180 degrees. So opposite angles are equal. That is the axiom. So when two lines intersect, we get actually 2 pairs of opposite angles, and each pair contains 2 equal angles. Correct? That is for 2 lines. We have covered 2 lines. Once we finish 2 lines, now we have to go on to 3 lines. Now we go to 3 lines and see what happens. Some very interesting things can happen with the 3 lines, right? Four. Again, we have different possibilities. Parallel, not parallel business is there, right? No questions on that. So we look at the first possibility for A. 2 lines parallel and third not parallel. So I got 2 parallel lines and a third line which is not parallel to either of these, correct? Or we can have 3 parallel lines, but 3 parallel lines are, they have no further interest for us because they look like 2 parallel lines. 2 parallel lines are like rail tracks, no, which never join. They always keep on going, right? So 2 lines, I've got 2 lines which are parallel. So let's draw 2 lines which are parallel. And a third line which is inclined to both of these, correct? When you do that, now you will see that for the pair of lines that you consider at these 2 points, the change of angle is the same. You can see that. That means I got 2 angles here which are known as corresponding angles. They correspond to the same direction. That's why they are known as corresponding angles. Actually, there are 2 pairs of corresponding angles. One on this right side and the other one on the left side. So I got a corresponding pair of corresponding angles to the left also. And that is also an equal pair. So you got 2 pairs. Each pair has 2 equal angles of corresponding angles. And if you take one corresponding angle, also has got an opposite angle. Because now here I got 2 lines intersecting and I got an opposite angle, correct? Which is equal. Now if you take these 3 angles, I got 2 corresponding angles. One of the corresponding angles has got an alternate angle which is also equal. So now I got these 2 angles, right, like on a Z that we write. You can see like Z, correct? So there is a change of direction, there is an opposite change of direction. That's why they are known as alternate angles. These are known as alternate. So when you have a parallel line and a line which goes across, we get a pair of alternate angles. And a pair of alternate angles is equal actually. And actually there are 2 pairs. There is one other pair also. If you want, I will show you here by extension. So the other side. This one and this angle. That's also alternate angles. No? So you got 2 pairs of alternate angles. And the 2 angles together both of them make 180 degrees. Because all angles on one line is 180 degrees. So that is that. So now when 2 lines are parallel, we get corresponding angles which are equal, alternating angles or alternate angles which are equal, which is very nice. Remember, this looks like a very simple diagram, but then when there is a big picture with lot of lines and circles and straight lines and so on, you have to visualize one small area of that picture and recognize there is one alternating angle there, there is one corresponding angle, pair of corresponding, you should be able to recognize. That is a deconstruction in your mind that you will have to be making. I'll show you some of the proofs where you will recognize. I'll show you that Z part of the picture by drawing it separately and show you also that they are the alternating angles which are definitely equal because of this particular axiom, right? So now first case is finished for A. Now we come to 4B. That is, no 2 lines are parallel. All 3 lines, we have 3 lines, no pair of them is parallel. So we have to draw 3 lines in all 3 separate directions is what I have to draw. And there is one special case of this is we draw 2 lines first, of course, as usual, which intersect at one point, and we draw a third line which also goes through the same point. So that is a special case. Third line can go anywhere. Third line can intersect the first line on any point, correct? But it happens to intersect at the point where the first line intersects the second line. These three lines, all of them passing through one single point, right? There are infinite number of third lines that I can draw, correct? But then I have drawn one specific set of lines, right? I can draw like this also, correct? Whatever, I have drawn that such that all the three lines intersect at one single point, not multiple points, and those lines are known as concurrent. They are called concurrent lines. Two lines are always concurrent because they are intersect at a point. Three lines to become concurrent, there must be some special property of the third line with respect to the properties of the first two lines, that it happens to pass through the intersection of the first two lines. That is concurrence or concurrent lines, correct? Then we come to 4C. It's the most general case of three lines. You can have any three directions and non-concurrent lines. You have to write non-concurrent lines. Let me just draw one example. I got one line here. I got another line here. I got a third line, right? And in this case, the number of intersecting points, there are 3 points here. Correct? And they form what is known as a triangle. So now I get a triangle. When three straight lines intersect at 3 different points, what I get is a triangle, which is very interesting. Triangle, I want to represent the triangle. I want to represent parts of the triangle. I have to give names to those 3 points. I've got 3 angles also. I have to give names for these angles. And I got 3 sides, which is the lengths of the 3 sides. Also, I have to give a name for those. And one popular method is to give symmetric names. And when you give symmetric names, when you write the proof theorem, or when you write the proof, or when you start deriving, you will find symmetric names always give you the next step without even thinking. I can write down the next step with no thinking. You understand? So you must always give symmetric names. For example, it was one person who is recognized as of today as one of the greatest mathematicians in the history of science. Plus, he is the greatest mathematician of 19th century. Right? He is Leonhard Euler. He gave quite a lot of these symbols, names to be used, and he proved a lot of theorems. He did work in so many different areas of mathematics. Euler has done work, infinite series, and you name it, his contribution has been there. So he is recognized as one of the greatest mathematicians in history, correct? And in fact, to pay homage to him, what we do is we give the first letter of his name as a name to the base of natural algorithms, E. What we call base of natural algorithms, or the number E as part of the real number system, is the first letter of his name. It's called E because of that. And he is the person who popularized the name pi to describe the ratio of circumference to diameter in a circle. That is pi, right? Pi d is the circumference. So pi, that name pi was given by him actually. Right? Pi, the second is a Greek letter. And third, he is the person who gave the name I, popularized the name I for storing an imaginary means you have to imagine. It's not there. You won't find it on the real line of root minus 1. He is the person who gave that. So, right? Now, according to him, when he say, I want to give names for these vertices, these are called vertices. So, a triangle has, if you look at a triangle, has 3 vertices. You can call them ABC or DEF, consecutive letters of the alphabet always. PQR, XYZ, whatever. So, but don't call them A, X, B or something. Don't give non-consecutive letters. That is not systematic. If you want to do systematic writing, for example, you can call them A, B and C as 3 consecutive letters of the English alphabet. A good way of calling that. And what about the angles in those corresponding places? One old method was to use the Greek symbols alpha, beta, gamma. So that means the 3 corresponding letters, first 3 letters. Alpha is the angle subtended at vertex A, beta is the angle subtended at B, and gamma is the angle subtended at C, is one way. But then people found really there won't be any confusion if you give the angle also the same name. So you can give the same name A. So A means either the vertex A or the angle subtended by BC at A. Both are A only. So ABC. ABC are the angles also. Depending on the context, you can decide what we are talking about is the vertex or we are talking about the angle. No problem there. Then we come to the sides, side lengths. Length of BC, you can call it BC if you want. One way of saying what is the length of BC? BC. BC itself is that length of the real line between points B and C is one way. Other way is to give a letter for it again. So when you want to give a letter for it, don't call it B, because B only signifies one part of that side. We need to have a combination of B and C together in that one letter is not possible. So the way is, so what is unique to this side in terms of one vertex? Actually what we are looking at is, just like angle A, this angle we called it A because it is unique with respect to the vertex A, so we called it A. Same way, if you look at BC, length of BC if you want should be something unique to the both the vertices B and C, right, is opposite vertex A. Both are opposite vertex A, right? So opposite vertex actually. So we call it A itself, lowercase. So side BC is called A, measurement. A is the length of BC. Similarly, what will be AC will be called B and AB will be called C, lowercase c. So ABC are the sides. But A is not the side at A. A is the side for BC actually, because that is what makes it unique. Now this combination if you use for the numbering or the naming of the vertices, 3 vertices, and we have 3 angles and 3 sides. Everything is 3 in the case of triangle. No? So obviously life is simpler when you write with those symbols. Many of the proofs look very symmetric. So we are looking at some kind of symmetry. So symmetry is very important. I will show you a couple of examples of symmetry as we progress, and you will be able to appreciate what I am talking about right now when I show you those aspects of symmetry, correct? So that is very nice. Now we can go further than triangles and we go to quadrilaterals. Next is item number 5, 4 lines. So when you have 4 lines, what can we do? So you got 2 pairs of 2 lines each, correct? Now each pair can be parallel, of course. So now that means I got 2 pairs, each containing a pair of, each is a pair of parallel lines. So I got 2 parallel lines. I got 2 other parallel lines, right, which are not parallel to these. Correct. And what you get as the 4 points, four-sided figure is known as a quadrilateral. And this particular shape where the opposite sides are parallel is a parallelogram. Now in the parallelogram you can see, it's very easy to see, there are a couple of corresponding angles. If you want, I will show you, right? For these 2 parallel lines and this one line, I got 2 corresponding angles which are equal. Similarly, for these 2 parallel lines and this line, I got alternating angle here. All 3 are equal, which means opposite angles of a parallelogram are equal. So I got 2 pairs. You understand? You can state that as a theorem or a lemma or whatever. Opposite angles are equal. That is a parallelogram. Similarly, opposite sides are also equal. That I may not be able to prove it right now, but you can take it as an axiom. Later on we can even provide a proof for it. Opposite sides are equal, opposite angles are also equal to each other. Okay. Then there is a special case of this. This is 5a. There is a special case of 5a which you can call it 5aa. What is that? These are not just two parallel lines, two pairs of parallel lines intersecting, but intersecting at right angles. That means the two opposite angles that you see which are equal are exactly 90 degrees. Other two opposite angles are also 90 degrees. So we got 490 degrees as the four angles of this particular shape. In this case, this is known as a rectangle. Now rectangle, you can see, has got two parallel lines and a vertical distance. Therefore, that distance is the minimum distance is same. So opposite sides are also equal. So opposite sides are equal, opposite angles are equal, opposite angles are 90 degrees. So that is a rectangle. And one subcase of this 5AA, you can call it 5AB if you want, is the two sides are also equal. That means opposite sides and adjacent sides both are equal. So you got all the four sides equal, all four angles equal to 90 degrees is what you get as a square. It's a square. That's the fourth shape or third shape in quadrilateral. Third shape, three special shapes. And of course, the main case is we don't have this parallel business. That means I have two lines every which way and two other lines every which way. Correct? So what I get is a proper quadrilateral. Correct? Proper quadrilateral. And quadrilateral, one couple of constructions that you can imagine is you can have some additional lines. I got 4 points there which are joined together. But now point 1 is joined to point 2, which is joined to point 3, which is joined to point 4, which is also joined to point 1, right? So each point is joined to two other points, but there's one point which is not joined. We can join it and see what happens. So I can draw this intervening lines. They're actually called diagonals. So I got diagonals for a quadrilateral which join the opposite vertices. Correct? And if you look at the special cases of rectangle or a square and so on, diagonals will have one particular property that you can discover on your own. Let's not bother about that. But diagonals also have a very special property in terms of theorem that we will discuss at a later stage. So that is the diagonal. So quadrilateral is there. Then you can go for pentagons, 5 shapes, 5-sided figures, then hexagon, 6-sided figures, heptagon, 7-sided figure, octagon, 8-sided figure, decagon, 10-sided figure, and so on. Okay, not a big deal. But then when you say I've got a, for example, I've got a pentagon or something, right? 5-sided figure. Now study of this pentagon, we may actually not even study that as a pentagon at all. We study that as 3 triangles. No? You understand? All you have to do is join. Remember, each point has got 2 diagonals now. In the case of pentagon, 2 additional points to which I can join. No? So now these 2 lines divide the pentagon itself into 3 different triangles. And if I know the properties of each of these triangles very well, I know the property of the pentagon. So I don't need to study pentagon as a separate shape. All I need to do is study triangle very thoroughly and use the same properties to describe pentagon or even a quadrilateral. Quadrilateral is 2 triangles. Pentagon is 3 triangles. Hexagon is 4 triangles, like that. You understand? So that means our entire geometry can be based on studying only triangles. Basically, triangle becomes the most important part of study of geometry because of that reason. Okay. And triangle, again, we have different classes of triangles. Actually, 3 classes of triangles which you can think of. One is known as a scalene triangle. Scalene triangle is nothing but an acute angle triangle. I will define the meaning of acute shortly. Then we have obtuse angle triangle. Lastly, we have right angle triangle. Basically, the entire classification is based on the fact that angle of a triangle can be less than 90 degrees or can be greater than 90 degrees or equal to 90 degrees. These are three cases. If one of the angles is, if all three angles are less than 90 degrees, then it is scalene or acute angle. Acute, that's known as an acute angle. Obtuse is wide angle. Obtuse is wide. Acute is narrow. So obtuse angle is, at least one of the angles is bigger than 90 degrees. I don't know whether two angles can be bigger, but I'm saying at least one of the angles must be. And right angle triangle, 90 degrees is known as right angle. No? The right angle. No? So that is the right angle triangle. Is one of the angles is 90 degrees. So that triangle is known as a right angled triangle. Now first thing we need to study is about the angles of the triangle. No? I got any triangle, doesn't matter whether it is scalene, right angled or obtuse angled. So what about the angles of a triangle? Can we make one observation on that? Is a question, is the first theorem in geometry, actually speaking. The first theorem is, I'll state it as a theorem. The three angles of the triangle, of course, add to 180 degrees. Total is always 180 degrees. Now, how do we prove that? We have to prove it now. So, we draw a triangle. This is the original picture which is there, right? Now, if we need some kind of now we need to do construction. I mean, I can't say what is this A plus B plus, there is no way of saying what is it going to be, right? No way of, unless I measure it with the actual compass, I can't say. I want to be able to prove it without measurement. How do we do that? There's nothing I can say about this. So if you want some kind of corresponding angles, some kind of alternating angles, you need to have parallel lines. Parallel lines and interesting line is what are going to give you corresponding angles and alternating angles, right? So we need a parallel line somewhere. So what we will do is, on the vertex A, so you got three vertices A, B and C, we draw a line which is parallel to BC. Simple. Construction is very simple. We just draw one line which is parallel. Very simple. So now, do we have alternate angles? Visualize a Z. Alternate means you have to visualize a Z or an inverted Z. Is there? Yes, I can see one Z here. And I can see one inverted Z here also. Correct? So therefore, you mark off those angles as equal. How do we do that? For equal angles, we use the same number of arcs to say they are equal. For example, on B, I will write one arc. On the alternative angle for B, I will write one arc. That means they are equal. The single arc equal angles. Similarly, angle C, I will write not one arc but two arcs. Because it may not be same as B. It may be equal. Maybe equal, may not be equal also. Doesn't matter. So it's a different angle. Then there is an alternating angle for C also, which is here, correct? And we have a third angle, which is A. There are three angles. B and C is over. Now I have E. If you want, I will draw three lines here. Now I don't have any angle equal to these three lines, correct? Right? Now if you say, I want to add the three angles of a triangle, actually what I want is A plus B plus C. Correct? No, this is not a vertex. This is an angle because I am doing an addition. I can't add a vertex A to vertex B, but I can add an angle A to angle B. So meaning is clear from the context that I want to add these three angles. A plus B plus C is what I want to add. A, we don't have anything for A, we leave it as it is. B, we take the corresponding alternating angle. For C, we substitute the corresponding alternating angle and add. So it will be the sum of these three angles. You can see that, correct? And that is one side of a line. On one side of a line, two directions, pull one side is 180 degrees because this is half of 360 degrees. Therefore, A plus B plus C equals 180 degrees. proof is one line proof actually, because of that particular construction. And I was able to do the construction, or I did the construction, because I wanted some angles to match, some corresponding, some alternate. You have to draw parallel. Basically, you have to draw some parallel lines. Yeah. I have found in geometry, most of the time, you draw some parallel lines or perpendicular lines, Then you get your alternate angle and so on and so forth. Correct. Now, this 180 degrees also gives you one very important property for, that is theorem 2, or you can call it a corollary. It is not really a theorem. A corollary is sum of non-right angles of a right angle triangle. That is equals, that means I've got a right angle triangle. Right angle triangle says one angle is 90 degrees. So I got 190 degree here, correct? 90 degree we normally write as a small square, not an arc. That small rectangle, when you write in a diagram, it says this is a 90 degrees. I don't have to specifically write 90 across that. It is a 90 degree, correct? So when you have this one right angle and I got two other angles, all I am saying is what is the sum of the two other angles, non-right angles of the right angle triangle. We know from the theorem that all three angles add up to 180 degrees, out of which 90 degrees is the right angle. Therefore, the other two must add to 90 degrees. So they are actually known as complementary angles. So when you have got two angles, they are called complementary because they complement 90 degrees. So they are called complementary angles. Similarly, when I have two angles on the opposite directions, any two angles, right, which add up to 180 degrees, they are actually called supplementary angles. These are just words, just names actually. There is no new knowledge there, just a way of writing. Saying got two supplementary angles means they add up to 180 degrees. Complementary angles means they add up to 90 degrees. So right angle triangle, the two non-right angles add up to 90 degrees is a corollary for this. Now you may say this is a corollary, but the importance of this corollary, I'll show you. Something phenomenal you will get out of that. I'll show you one example which we might probably use later on. Supposing I have got a right angle triangle. I'll give proper names to the vertex so I can refer to the angles. A, B, C. And B contains the right angle. Angle B is the right angle. Now, construction is we drop a perpendicular from B onto AC. That means I get a new point, which is a constructed point, is a point D on this line AC. Line AC is also known as the hypotenuse. These are two sides of the right angle and is the hypotenuse of the right angle. So we drop a perpendicular from this onto the hypotenuse. I get a D, correct? Now, if you see some of these angles in this, now I got, how many triangles I have? I have three triangles, not two. I got three triangles. And what are the names of the three triangles? I had originally, of course, ABC. I had a triangle ABC. We write it like that. Delta ABC. It's a triangle ABC. Now I also have a triangle ABD. It's a triangle. And I also have a triangle BDC. So I've got three triangles actually in this diagram. Just by drawing one line in the center, I've generated three triangles. And three triangles have some very interesting properties. If you look at the angles, for example, I got a C, correct? This angle C is one of the angles of the right angle triangle BDC. Remember, all three are right angled. In this case, ABC is right angled with a right angle at B, ABD is right angled at D, BDC is right angled at D, correct? Now, angle C is one angle of this right angle triangle. Therefore, this is complementary to, how do we write that? They are equal actually, right? How do I write that? angle I can write is BCD. You write that as angle BCD. BCD or BCA, both are same. BCD and BCA are same. Is equal to, is actually is a complement. Is a complement of, that is 90 degree minus DBC. Correct? They are complements of each other. So they add to 90 degrees. But we also find, I got another angle here, which is also a complement of BDC, right? Because this is also 90 degrees. Which means, (90 degree minus DBC is ABD. So that means this angle is angle C. Right? The same. It doesn't look like it, but they're same. They're same. So we'll use this factor. In fact, Einstein, the first person to do this construction for this particular purpose of proving Pythagoras Theorem. You can prove Pythagoras Theorem using this construction, and the only construction is draw one perpendicular from onto the hypotenuse, where you get three triangles, all are right angled. We'll see that proof later on, of course. That's not the first theorem that we want to prove. There is an earlier theorem that I want to prove from the father of mathematics. Who was the father of mathematics? Thales, not Pythagoras. Father of geometry was Thales. Now, Thales gave one theorem which is probably one of the most fundamental theorems in geometry, more fundamental than Pythagoras theorem. He is on what are called similar triangles. So we give a definition first for what are similar triangles. No? What are similar triangles? Triangles which look similar. Triangles which look dissimilar are not similar triangles. No? They have to look similar. No? What is that similar? I have one triangle. Let me draw that. Then you will see what I am talking about. So I have one triangle here. You can call it ABC if you want. Correct. I'll draw one more triangle on the side. DEF, right? If you want, I'll draw a third triangle, which is GHI. Now, if you consider the two triangles ABC and GHI, do they look similar? They don't. They look totally different, right? Whereas when you look at ABC and DEF, they look similar. So they look similar. That's why they are known as similar triangles. And the definition is very simple. Angles are same. Angles are equal. Similar triangles have three angles equal to the three angles of the other triangle. So in this case, for example, the angle at B is same as angle at E. Angle at A is same as angle at D. Angle at C is same as angle at F. Correct? So when you have three angles same for two triangles, they are called similar triangles. And intuitively, if you see that EF is actually longer than BC, you can see that EF is longer than BC. Assume that EF is twice the length of BC. You would find that DE would be twice the length of AB and DF will be twice the length of AC. You can see that the side lengths for similar triangles, when you increase in size, they grow proportionally. So they increase proportionally. So the theorem, which is Thales' theorem, I will state that. Very simple theorem to state. Similar triangles have proportional sides. So similar triangles have proportional sides, but unfortunately to prove Thales' theorem, we need to look at one additional set of axioms on areas of triangle. We never discussed areas of triangles. Let me just do that now shortly before we go on to actually prove Thales' theorem. What is the area? What is an area is a question. Is again just like we had a point on a plane. We are saying things of areas on a plane. So what is this area? And the simplest example I can think of is a rectangle. So take a rectangle which has 90 degrees, all the four angles are 90 degrees and is supposed to have a length and a height. Correct. I'll call them L and H, length and height of a rectangle, right? L is so many, whatever, real number. Initially I can have integer itself as a value for L. We'll have integer itself for value of H. That means L is probably 4 or something and H is 3 or something as an example, which means what I can do is I can take bricks. Brick size is 1 by 1 unit. 1 foot by 1 foot or 1 centimeter by 1 centimeter, whatever measurement that you use, 1 by 1 is a brick. So that means if you have an integral length of 4, I can fit exactly 4 bricks on the length. Correct? No? I can fit 4 bricks. Same way, because the height is 3, I can fit 3 bricks on the height, which is 1 by 1. But I got other places where I can fit the bricks. So, correct? No? So how many bricks, how many 1 by 1 bricks that I have fitted into this rectangle will be exactly equal to L multiplied by H. LH multiply length by height will give you the number of bricks that I can fit into that, provided L and H are integers. But we'll assume it is true for all real numbers. It's just an assumption, axiom if you want to call it, is that area of a rectangle is equal to length multiplied by height. We'll assume that statement as correct. We can state that as an axiom, saying area of a rectangle is length multiplied by height. Okay, very interesting. We come with one corollary for that, so that is the axiom. Area of rectangle is length multiplied by height. What is the corollary? You take any rectangle. We know the area already because I got a length and a height, no problem. But then I need to derive something from it. Remember, study of any diagrams beyond 3 sides, we always try to break it up into several triangles. And how do I break up this rectangle into a couple of triangles? Is to draw one diagonal. Draw a diagonal. When you draw the diagonal, now you can see I got 2 triangles. Both of them are actually identical in size because they have a common hypotenuse and the opposite sides are equal for rectangle. Therefore, this also has got a height of H, length L, and this length of the hypotenuse, correct? So we have got 2 triangles which are actually known as congruent. So if you want to call this ABCD as the name of the rectangle, I got triangle ABD which is congruent to triangle CDB. Okay. Now congruence is much stronger than similarity. Similarity only angles are equal. Here angles are equal, sides are also equal, known as congruent triangles. Now I got 2 triangles which are congruent, which means they are identical. Yeah? They are same, no? Same in size, same shape, everything is same. Similar is only shape is same. Here size also is same. Shall we assume that they have the same area? Is the assumption I will make. So these 2 triangles, let us assume they have the same area, and when you add these 2 equal areas, I get the area of the rectangle. Therefore, what is the area of triangle ABD? Is half multiplied by length multiplied by height. Correct now? Is half of the area of the rectangle. So half of a rectangle triangle is half the length multiplied by height, perpendicular height. So that is, because there is a 90 degree, you can always take a length and the height. Because of 90 degrees. Don't have 90 degrees, you can't do this. It's only true for right angle triangles. What equation I have written is only for right angle triangles. But then what about scalene triangles, and how do you find area for scalene triangles? Let us take a look at that as the next theorem. Area of any triangle. Supposing I have a triangle, usually we call it ABC. None of these angles are 90 degrees. But then to make use of our earlier results, we need a rectangle at least, or at least we need a triangle which is right angle. No? Without that I can't use this. So what is the construction that we want to make? Perpendicular, correct? We try perpendicular. So what is the area of triangle ABC is what we wanted. Is now I got two other triangles here. Area of triangle ABD plus area of triangle ADC. Correct? I got two right angle triangles. I add the areas of these two, I get the area of the original triangle. Now what is the area of triangle ABD? I can find out very easily because it's a right angle triangle, right? So for the right angle triangle, remember, we need to have something called the height. So I'll call AD as the height. So what is this? This is half multiplied by length, which is BD, multiplied by height, H, or you can call it AD also. Half BD multiplied by AD will be the area of triangle ABD, because that is a right angle triangle. Plus same way for ADC, what is the area is half multiplied by DC multiplied by AD. Correct? Half length multiplied by height. Correct? When you add these two, so is I can take common factor here. Half AD is common. So half AD multiplied by BD plus DC. And what is BD plus DC? BC. Correct. Simple. So, what is the area of triangle ABC? Is half into length. We call it a base now. It's not a length because it's not a rectangle or it's not a rectangle triangle. So, the BC is known as the base. And AD is known as the height. Height is actually the height from the base to the vertex is the height. That is the perpendicular height. So, half into base into height is the area of any triangle. Now, unfortunately, I had drawn one scalene triangle which all had angles which are less than 90 degrees. Therefore, this construction happened. But we should be very careful when you do such constructions, that there is always a possibility that diagram may look totally different when you do the construction. I'll give you a different thing. Same construction, my triangle is different. So, my triangle ABC looks like this now. Is an obtuse angle triangle. So we take an obtuse angle triangle, same ABC, right? Now, when I draw the perpendicular from A onto the line BC, it is not going to fall on the BC, but it is going to fall on the extended line. Correct? Now, if you add the areas of these two triangles, you are not going to get the area of the triangle that you want. You understand? So, be very careful. So, this is one picture, but easily I could have had this picture. In this case, now we will write. What is area of triangle ABC is what we want, of course. But then, it's not the sum of the other two or whatever like we had before, equal to, what is it? area of triangle ADC, here we added, we did the area of triangle ADC plus ABD, no? That's not going to happen. It is ADC minus area of triangle ADP. You understand? We take this big triangle and subtract the smaller triangle. Both are right angled. The big triangle ADC is also right angled because we have 90 degrees. And the small triangle ADB is also right angled because we have 90 degrees. And we subtract the smaller triangle from the bigger triangle, we get the area of triangle ABC. Correct? So instead of plus, actually all we have is, in this diagram, if the diagram were like this, you cannot write plus there, you have to write a minus. Same, statement is the same, but with a minus sign, correct? So now we'll write down, what is this? Area of triangle ADC is half DC multiplied by AD, correct? Half base and height, minus area of triangle ADB is half multiplied by DB multiplied by AD. Again we take the same common factor, half AD multiplied by DC minus DB. What is DC minus DB will be BC. So is half AD multiplied by BC, or BC multiplied by AD. So half into base into height. In this case also that statement is true. In all cases, area of a triangle is always half base multiplied by height. Correct. So now this diagram, this obtuse triangle that I wrote, and we calculate the area of this triangle, you should keep it in your mind. It should get recorded in your mind, because tomorrow in some of the proofs that you're going to see, you will find this as part of the diagram. That means, let me probably state a couple of lemmas to prove my point. I have this obtuse angle triangle. Right. Now what you do is you draw a line parallel to the base through the vertex. Now I have a base BC. I'm not going to touch this base. Fixed. Base is fixed, yeah. We will not touch it. Base is fixed. Now I got a vertex A which happens to be at this place, right? Supposing I start shifting the vertex A on the parallel line, what is going to happen is a question. So for example, I shift it to somewhere here. So I get a triangle, a new triangle, which will look like this. So this point may be D. So now I got two triangles here, ABC and DBC, correct? Both are sitting on the same base. Base is common. And both are between the same two parallel lines. Height is common. Area must be equal. So when you have two triangles on the same base between two parallel lines, area is same. Area never changes. Actually, you can move the point A anywhere on this parallel line. Area of ABC will remain fixed. So that you have to keep that in mind. So when you look at a triangle, you should visualize moving the vertex and see, do you get something new, or do you get some idea, and so on. No? So we have to see that very carefully. Okay, that clear. So now we go and prove Pythagoras theorem. We are ready for Pythagoras. After all, Pythagoras theorem is talking of areas, right? So we have area on the two sides of the squares. Squares on the two sides is equal to area on the square of the hypotenuse. That actually area, squared is area. No? So area of a square is square of that side, correct? Square is a special case of rectangle where the length and height are same. So L square. So area of a square is always the square of that side. So we got three areas there, three squares there, three areas there. So entire Pythagoras theorem you should be able to prove using the area rules, and especially this one diagram should help us in proving Pythagoras theorem using areas. Pythagoras theorem has been proved in 1,000 different ways. People have provided proofs. I am going to look at three proofs only. Why three proofs, you might ask. The reason is very simple. I could have looked at all the 1,000 proofs, which is It's not possible. I could have just looked at one proof, but then we are not just interested in the proving this Pythagoras theorem. We want to look at the method to use the proof, right? So I have selected three totally different methods which can prove Pythagoras theorem, or three different methods. Okay, we'll take three proofs. They use totally different techniques of deconstruction and construction and proof. So that you get familiar with the different methods for the same theorem. Theorem can be same or different, correct? So we'd like to look at the first method, which probably Pythagoras never gave it. I think Euclid gave this proof, it doesn't matter. Probably this proof was known to Indians before that, and definitely Babylonians knew this proof of Pythagoras theorem at least 1500 years before Pythagoras, guaranteed. I'll give it to you in writing, they knew that, so no problem. So now I'll give you MLS Shastry's proof, which is the same actually, which was given by, what proof I am giving you was probably known to Babylonians 3800 years back, if that helps you understand the background, of what we are discussing. So we'll take a triangle and try to prove using areas, right? So I'll give the first proof. Proof number 1 for Pythagoras theorem. So we start with a right angle triangle. Always write it with sides which are not equal. Don't write an isosceles triangle. No? Isosceles triangle is a triangle with two equal sides. Equilateral triangle is a triangle with three equal sides. No? So anyway, right angle triangle can never be equilateral. It can be isosceles. These two sides can be same, but the hypotenuse definitely is not going to be the same. No? So it's going to be bigger than either of them. So don't write an isosceles triangle. Then your diagrams you may feel, oh, this is like that. It may not be equal. So always write a triangle which has different sides, noticeably different lengths. No? Noticeably different lengths. Now, our question is, we need to construct the squares. Now, what is actually as part of the theorem? Actually, I am supposed to write the squares on all the three sides. No? So I can write that, of course. I can write a square on this one side. I have to write with full line because it is not construction. It is actually as per the original theorem itself. No? Square on the two sides add up to area. Areas of the two sides squares adds up to area on the hypotenuse, right? So I have to actually draw the three squares. You can see hypotenuse has got a bigger square, right? So Pythagoras theorem states that I got three squares here. You add up the areas of these two squares, will add up to the area of the third square. Right? Yeah, but now already I have cluttered up this diagram for my vision. You understand? It becomes difficult to visualize basically. I want you to visualize a part of this picture, so I have to do deconstruction, right? What is deconstruction? Rub out parts of it. Actually. Then we do construction, right? So what is my interest? I don't want to actually construct all these three squares. First is, I am looking at only one side here. Let me remove the other side completely. I am not even interested in it. So what is the deconstruction? Like I said, I'm not going to bother about one side. I'm going to look at one side only. So I removed the entire square on the other side, right? Similarly, this full square also, I don't even want to look at the full square because then my vision gets cluttered up with so many lines, So I want to improve the quality of my vision perspective, So I will draw only one side, actually one side. Other side I can show some dashed line or something like that. Similarly, on the hypotenuse, I don't want to draw the entire square on the hypotenuse. I'll draw only one side, and the other side I will show a dashed line. But I have drawn it equal, of course. That means, now you see, what I have done reconstruction is, I have the original triangle ABC, we start giving names to these vertices. So I got an A here, B here, and a C here. Right. Now I have drawn part of the square on the hypotenuse, I have drawn a point we'll call it D, which is perpendicular to AC and same length as AC. AC equal to CD. One line I have drawn. Similarly, from C I have drawn a line perpendicular to BC, and that is a point E. Correct. Now, if you look at the four lines, now you have to make the construction now. You look at the four lines. I've got, other than AB, in fact, I can even rub this connection itself. If you want, I can rub it or maybe make it dash line. So, now you see four solid lines that you see is what you want to see in the original diagram, really speaking, is I got AC, I got CD, both are equal, AC equal to CD. So, let me write that down. And angle ACD is equal to 90 degrees, is right angle, because this is part of the square. Similarly, I got BC equal to CE and angle BCE is 90 degrees. Correct? So I got two angles which are 90 degrees and two sides which are equal to each other. Now, I want you to look at triangles out of which I am showing only two sides. The other side you have to visualize. And I want them to be similar or congruent or something so you can compare the areas. I can't take AC and CD, try to compare with this because they are totally different. So what you should do is, let me draw those lines. Take BC as one side, CD as another side for a triangle. That means one side is equal to one side of the original triangle, other side is equal to hypotenuse of the original triangle. This is one. Same way, I will take CE as one side and AC as the other side for another triangle. This also has the same two sides. So you can see CE is also the original side of one side and CA is the hypotenuse. So now if you think of two triangles of these, that is triangle ACE and BCD, if you see, two sides are equal. Correct? And now what is the angles? Now you have to look at angles. Angles also, BCD has got this angle BCD. Right? So angle BCD. And ACE has got right? Now you see, both these angles are made up of 190 degrees and a common angle. Correct? In fact, I can write it down. Angle BCD is equal to angle BCA plus angle ACD. BCA plus ACD is BCD. Similarly, angle ACE is equal to angle ACB plus angle BCE. Correct? The triangles are same. So now I got two triangles which got two sides which are equal and the subtending angle also is equal. They are congruent. In fact, I didn't make that as a statement or a theorem. We should have made that statement, or you can state it right now as a lemma. Lemma is when do two triangles are congruent? There are three possibilities that you think of. So, lemma on congruence of triangles. I should have done this earlier, but at least I am doing it now. Okay, congruence of triangle. So, first case is three sides equal. All three sides are equal, they are congruent. B, these three sides equal, side is known as S. It's called the SSS lemma. SSS, side, equal to side. No? So that is SSS. Then we have SAS lemma, that is two sides and subtended angle are equal. That means actually I got one side, another side, and the angle is same. Obviously they will be congruent. Okay? That is known as SAS, side angle side. And case 3 is angle side angle, ASA. That means From one side, I take one angle and draw one side, and that side itself is matching. From there, I draw another angle. So these two angles on a base. Base is common, two angles on the base are same, two triangles are congruent. So in this case, I have two bases, two bases actually, two sides. That is AC and CE are two sides. In the other triangle, I have CD and BC as two sides, and the subtending angle SAS in between. The two angles are same, right? So which means they are identical triangles. They must have same area, right? So now we do the construction. Now deconstruction is complete. Understanding or looking at the picture is complete. What is the construction is to complete these triangles. So I will join B to D as one line, completing this triangle BCD. Similarly, I join A to E. So completed this triangle, right? So now, if you look at the area of BCD, assume CD is the base and B is the vertex. You got a triangle, no? And start moving this vertex parallel to the base, just like I showed you that diagram, no? So imagine this diagram. BC is the same as CD here, and this vertex A is B here, and we move B in a line which is parallel to CD. That parallel to CD is nothing but the perpendicular line, right? So we draw that line. Correct? So now you can see I got a triangle sitting on a base, and I got a rectangle sitting on the same base and the same height. Therefore, area of the triangle must be half of the area of the rectangle. Same way, if you look at the other triangle here, I got triangle ACE. Now imagine CE as the base and A as the vertex, and we move A on the parallel line to CE, parallel line, which means now you can see if I move till B, I get a triangle which is BC. I'm moving this like this. Just visualize this triangle. I'm moving the vertex A like this down, which means area of this triangle will become exactly half of this rectangle, which is actually a square, half the area of the square. Right? So I can write that in detail, but I'll assume that you understand what I have said. Let's just write that picture here. So area of triangle BCD is equal to half area of this rectangle, right? Rectangle, I need to point for this perpendicular, we'll call it H. Right? Half area of rectangle, which is half base into height, CD multiplied by CH. Similarly, area of triangle ACE is half area of square. That's also rectangle, but we'll call it square. This triangle, just move that vertex down, I get a square here. So square equal to half multiplied by CE multiplied by BC. Both are same actually, it's a square, right? And these two triangles are congruent, I told you. Therefore, these two areas are same, right? Which means I can write CD, which is same as AC, because that was the square, no? So AC multiplied by CH equals BC square. BC and CE both are BC, correct? Because that was the square we started with, equal to BC square. AC multiplied by, that means the hypotenuse multiplied by part of the hypotenuse is equal to the square on one side. Now, by symmetry, now you have to use symmetry in your mind, correct? What I must get is by symmetry. I'll just write it. You can verify by constructing the appropriate triangles. We can say AC multiplied by AH will be AB square. hypotenuse multiplied by this part will be this square. And add these two. AC multiplied by CH plus AH, which is AC. AC square. This is AC square equal to BC square plus AB square is Pythagoras theorem. So you get Pythagoras theorem. So now you see Pythagoras theorem we proved by saying I have split this hypotenuse square into two rectangles. One rectangle area will match with the area of one square, other rectangle area will match with the other square. That is the principle that I used. And we have proved Pythagoras theorem. Is that clear? So I would like to stop there. There are two other proofs of Pythagoras theorem I would like to discuss before we go on to prove Thales theorem. Actually, I should have proved Thales theorem first because that is even more fundamental. It doesn't matter. I went in some order and it has happened. Now, there is nothing we can do about that. I can't take back Pythagoras now. Thales is older, 200 years older than Pythagoras. But anyway, we'll go back in history and see how Thales proved his theorem about similar triangles. That is, similar triangles have proportional sides, correct? So that is what we want to prove next. Thank you.